Hello there and welcome to video number 10 of our computer science series. This is actually video number 2 of our logical operations chapter, and today we will be looking at the laws and the rules of Boolean algebra. Now these rules and laws will help you simplify the Boolean expressions that we'll see in the next video. Logic really does apply in this chapter, and it's important that we go back to our fundamentals, our 0 and our 1 being our electrical on and off switch. Always go back to that and think in the simplest possible terms. And finally, it's really important that you practice these rules and these laws. It's going to massively help you if you can recall these from memory to simplify your Boolean expressions. So how do I remember all of these rules off by heart? Because that's what we're going to start with. We're going to start with the rules. I separate all my rules into groups. My first group being the AND rules. The first AND rule we're going to look at is A and 0. The next one is A and 1. Number 3 is A and A. And number 4 is A and not A. So what I want you to do is I want you to think as if A has two inputs. A can be 0 or A can be 1. If I AND those values with 0, you should be able to remember the truth table that states both conditions need to be 1 in order for my output to be 1. So in this case, because I've got two conditions that contain a 0, that means my output will always be 0. So for number 2, I have two conditions. My first condition is 0 and 1. My second condition is 1 and 1. And because I've got a constant of 1, A dictates if it's true or false, so A and 1 equals A. For number 3, my first condition is 0 and 0 because A can be 1 or 0, and my second condition is 1 and 1. So my final answer will always depend on whatever the input of A actually is, meaning that A and A equals A. When trying to get students to understand this logic, I basically say to them, if you've got a cat and a cat, you've always got a cat. For number 4, my two inputs are 0 and 1, and my second input is 1 and 0. And if I AND those together, it gives me 0. Remember, when there's a bar on top of my letter, I basically flip the input. For my second set of inputs, you need to remember the OR truth table because these are my OR rules. The OR truth table dictates that any one of my inputs that has a 1 will return 1. So let's have a look at our OR rules. Number 5 is A or 0. Number 6 is A or 1. Number 7 is A or A. And number 8 is A or not A. Now don't forget again that A can be 0 or 1. So for number 5, I'm going to write 1 or 0, and my second term will be 0 or 0. And if I work that out in my OR truth table, A or 0 will return or simplify down to just A. My two terms for question number 6 will be 0 or 1 and 1 or 1. Apologies that you can't really see that, but I promise you it's there. Then I put that in my OR truth table, and each time I run that, it returns 1 because there's always 1 present in both of my conditions there, so I get 1 returned. My inputs for number 7 are 0 or 0 and 1 or 1. And that will return A because it all depends on the condition that I put in. For number 8, my two conditions are 0 or 1 because I flipped the input. For number 8, my conditions are 0 or 1 because I flipped the original input of 0 to become 1. And then if I put in 1 as my original input and I flip that, it becomes 0, giving me 1 or 0. If I run them in my OR truth table, it will always return 1. For number 9, we look at negation. If you see a double bar above an input, such as A, that will show you double negation. If I input 0 and flip it for the first negation bar, it becomes 1. Then I flip it again, it returns back to the original data. If I put a 1 as the input, the first negation bar flips it to 0, and the second negation bar flips it to 1, giving me the original input again. So we can say that a double knotted A just returns A. Now we could stop there, but these rules will seriously help you and save you so much time when you are simplifying your expressions. Now, they might require a little bit more proving, but stick with me, and if you're unsure, rewind the video, go over it again. So what we've said here for number 10 is that A or A and B equals A. Now, it's important to point out here that you can't see a AND symbol in between the A and B yet. Sometimes notation is written without the AND symbol, the full stop that we use, but we can assume that it is there. Now, if what I'm about to do blows your mind a little bit, there's absolutely no reason why you need to be able to prove these as they've already been proven. However, you can just remember that A or A and B equals A if you want to. You don't have to prove it. I'm just showing it just so you can get an idea of how we do it. So the first thing that I'm doing is I am removing one of the A's out of the term. I do this by factorizing, which is the opposite of expanding my brackets, or distributing my brackets, should I say. And when I say terms, I mean A is my first term, or A and B is my second term. So now I've factorized it. If I was to distribute my brackets, I would do A times 1 and A times by B. And that would give me the term A and 1 or A and B. And this is an important step because A and 1, as we looked at before, will always produce A. And the second part of our term would be or A and B. So let's go back and finish proving this. I left with A inside the brackets, 1 or B. As we looked at before, 1 or B will just give us 1. And this is because we are applying our identities or our rules that we looked at before. And I'll point out that it doesn't matter which way round you do these. You can have A or 1, which equals 1, or B or 1, which equals 1 as well. Or you can swap them round and have 1 or B, that will equal 1. Doesn't matter which way you write the term round, it will always be 1. And then if we AND A with 1, it will just produce A. And therefore proving that A or A and B cancels down to just A. So if you want to keep any of that, then that's completely up to you. But like I said, you don't need that. You can just remember that A or A and B is A. So let's look at number 11 then, where A or not A and B equals A and B. So looking at that, you might think, John, where have you got the extra A and B from? Well, basically, we've applied the previous rule, which allows us to bring back in the A or A and B. And by this I mean, you look at the A above, and because we derived A or A and B equals A, we've reversed that rule to give us some more terms. That makes it much easier for us to work this out. Next, we factor out B from the second and third term. So that enables us to remove B, which means we are left with A or not A in our brackets. And that means that, looking at our rules from before, A or not A gives us 1. And the final step, if we AND 1 with B, it'll return whatever the value of B is. Okay people, we're nearly there. We're on our last one now, number 12. And this rule says that A or B ANDed with A or C gives us A or B and C. And the first thing to do is multiply out the brackets. So I times A by A and A by C and B by A and B by C, which gives us A and A or A and C or A and B or B and C. And that's what we call distribution. It's sending everything out of the brackets. Next, we look for our sort of common things that we can apply, our rules. We have A and A, which we can simplify down to just A. Then I can use the law of absorption, which you've not seen before, which I'll show you on the next couple of slides. And I can use the law of absorption again, to cancel down A and B or B, which just gives me B. And that leaves us with A or B and C. And these rules are a little bit more odd, from 9 to 12, and I like to call those my miscellaneous rules. And some strategies for remembering these are to continue to apply them on lots of different questions, practice them, make flashcards if you need to, and just keep revising them. So now we've looked at the rules, let's have a look at some Boolean laws. And these laws can be applied to manipulate our Boolean expressions as well as our rules. So the first rule we need to look at is the commutative law, and that states that A and B is equivalent to B and A. And for our OR rule, A or B is equivalent to B or A. So that means we can basically just swap the terms round if we need to. Now again, these can be proven, however, I don't feel like there's a need to prove them as long as we remember them. Next is the associative law, and that states that A and inside the brackets B and C is equivalent to inside the brackets A and B with C anded outside. And the OR equivalent to this law says that A or inside the brackets B or C is exactly the same as inside the brackets A or B ORed with C. And all that means is that we can remove different terms inside and outside the bracket. Next is our law of distribution. And this shows that we can distribute our term into brackets. So for example, A or B and C can be distributed into brackets of A or B anded with A or C. For the OR term, you'd do A and B or C, and into brackets you would put A and B or A and C. And obviously you would put it in the brackets. Next we're going to talk about the law of absorption, which states that A and A or B is just equivalent to A. And this is a fantastic law to remember, and this is one that will come up time and time again in exam questions. And I'm going to prove this one using a truth table to prove to you that this is actually true. So I'm going to first write my inputs. I've got two different inputs, A and B, and I draw my normal truth table using 0, 0, 0, 1, 1, 0, and 1, 1. That gives me all the inputs that I can possibly have. Then I'm going to do the first bit of A or B, so I can OR the A and B column together, giving me 0, 1, 1, 1. And then all I need to do is AND that A or B column with the A column, and that gives me 0, 0, 1, 1. And you can see that the A column and the A and A or B column is exactly the same values. And from this we can derive that A and A or B is exactly the same as A. But what about this one? The law of absorption also applies for our OR terms. So A or A and B will produce just A. So let's have a look. The truth table again gets drawn as normal, A and B inputs, and we have 0, 0, 0, 1, 1, 0, and 1, 1. And from this, I'll do my A and B column. So I AND A and B together, give me 0, 0, 0, 1. Then all I need to do is OR the A column with A and B, and that gives me 0, 0, 1, and 1. And we can look again and see that, yep, both the same values are correct, and that means that A is the same as A or A and B. Okay, I promise you now this is the last part. We're going to quickly look at an A2 topic here. And we're going to look at this man, Augustus De Morgan, 1806 to 1871. He was a British mathematician and logician. A logician, not magician. Anyway, he created De Morgan's law, which states that not A or B is equivalent to not A and not B. And if we look at the AND terms, not A and B is equivalent to not A or not B. And the key rules to pick up here, if you get an exam question, which they often do appear, they ask you specifically to apply De Morgan's law. You will see an exam question with a bar above the terms. So for example, A or B with a bar across it will be not A or B. To apply De Morgan's law to this, you break the bar, which will give you not A or not be. And the second part is to change the sign. So if I had a or sign, I change it to an and if I add an and sign, I change it to an or. And that is applying De Morgan's law. But don't worry, that was just a very, very, very brief overview of Boolean rules and laws, including De Morgan's law. In the next video, what we will do is we'll look at some examples and we will go through them and try to apply the laws and the rules to see if we can simplify them. And thanks again for watching. I've been John and hopefully you will join me in the next video.